Oh, is it? Thank you. Let me just double check here. Thank you. Let me try it one more time. Better, hopefully. See the screen, I hope. Sorry about that. And, yep. Okay, good. Thank you for letting me know. So again, as I was saying, our type 1 and our type 2 are metals and non-metals. Our type 1, again, is these guys that contain these metals here. And basically what we do with those, as we talked about last time, is we want to go whole name of the metal, and then the non-metal will get the IDE at the end of it. And with our guys that are sort of the other type, are basically groups of nonmetals that are together, but they still have a charge. So, for example, if we look at something like NaNO3, or if we look at something like NH4NO3, for example, when we look at this guy here, the NH4NO3, this guy is actually made up of two polyatomic ions. This is basically NH4 plus, and this is NO3 minus. And again, what a polyatomic ion is basically a group of nonmetals that have charges. So they are groups of nonmetals. They basically stay together. So when we look at something like this NH4, this one nitrogen, those four hydrogens, they're all bonded together. They're actually sharing electrons and holds them together. They never break apart. They never fall apart into one nitrogen and four hydrogens or anything like that. They move around as that NH4 unit. And that entire unit only has a +1 charge. Same thing over here. This nitrogen and those three oxygens all again stay together as one unit. They have essentially only one type of charge, and that whole charge on that one nitrogen and three oxygens is that -1. And this polyatomic ion over here has a special name. It is what is known as the ammonium ion. And this guy over here is what is known as the nitrate ion. And these polyatomic ions, they have essentially um, individual names. They also have individual charges. So when we look at something like this, we are still putting together really like an ionic compound. So the charge on this NH4 is +1, charge on this NO3 is -1. So again, when we put it together, we want it to equal 0. And that means we just need one of each of those, which again is how we get to the formula that we see over there. We basically need one NH4, which is +1, one NO3, which is -1, +1 -1 gives you 0. And in terms of naming this, we actually would just use the polyatomic ions name. So we would start with ammonium. And the second polyatomic ion is nitrate. So this would be ammonium nitrate, and that would be the name of it. As we will see, for example, if we look over here where our NaNO3 is, also we could break it apart right there. This is our normal sodium, which is group 1, has a +1 charge. Again, this is our nitrate, which is our NO3 minus. Also, again, it stays together, has a -1 charge. Again, that is why it's +1 and -1 gives us just one of each of them that we need. So when we would name this, we would follow kind of the same rules. So this is sodium, which is group 1, has a fixed charge, which means we just need to use sodium. And again, here we would use the name of that guy, which is nitrate. So this would be known as sodium nitrate. Again, still a +1 -1 in terms of balancing out the charge. And as we'll see and as we'll talk about, that's essentially what will usually happen with our polyatomic ions. They will essentially be hooked up a lot of times with metals, because for the most part, as we'll see a table in just a second, this guy right here, which is the ammonium ion, is essentially your most common sort of positive polyatomic ion that you'll come across. He's the one that you'll see most of the time, and that means that most of them are negatives. So let's take a look at this list here. This list is basically a list of polyatomic ions, ones that have for example, a +1 charge. As you can see, ammonium is kind of the only one, and that 4 actually should be on the bottom here. Cross that out. There you go. So that's NH4 plus. And when we look at some of these rest of these here, these are all a bunch of our guys with -1s, guys -2s and -3s. So unfortunately, you do have to sort of know these. You do have to memorize these. And there's a couple of good ways that you could kind of go through this list and figure out, sort of how to memorize them. So when you look at a list like this, there's groups of polyatomic ions that are sort of related to each other. So for example, if we look at the NO3 minus that we saw earlier on the last page, there's also one that looks very much like it, which is NO2 minus. This guy is known as nitrate. This one is known as nitrite. Also, if you look, there's SO4 2 minus, which again means that one sulfur and those 4 oxygens are all bound together. They all stay together. They never break apart individually, and they all have a -2 charge. This is what is known as sulfate. And there's also one that is SO3 2 minus, also 1 sulfur and 3 oxygens, also stays together, never breaks apart. The SO3 unit stays together, has that -2 charge, and this is what is known as sulfite. So when we look at, for example, a group of 2 polyatomic ions that are related to each other, what we typically will see is this one has 3 oxygens, this one has 2 oxygens, for example. They both have -1 in terms of their charge. So the only real difference between these groups of 2 here is the number of oxygens. And the difference between the number of oxygens is the one that has the most oxygens in a group of 2 will end in 8. The one with the least number of oxygens will end in ite. So the most oxygens will typically end in 8, while the least number of oxygens will end in ite. And we see the same thing over here. The only difference between our SO4 and our SO3 is the number of oxygens. The one with the most oxygens ends in 8. The one with the least number of oxygens there ends in ite. So that's a very good way to sort of group these guys together. It allows you to sort of figure out, the actual names or remember the names by grouping them. And that's sort of the best way to do it. When you look at these and you go to sort of memorize these, it's important to memorize both the formula and the charge because you'll need to balance out everything. So it's really important to remember those. There's also some groups of 4 that you'll see on here, and probably the most common group of 4 is actually this group over here. Just move some of these boxes out of my way here so I can see it. Over here, this group right here. And that is this group of 4 is probably the most common sort of grouping of 4 that you will see. And in terms of that, we have something that is ClO4 minus, ClO3 minus, ClO2 minus, and ClO minus. All of these guys, again, the 1 chlorine and the 4 oxygens there, the 1 chlorine and the 3 oxygens, 1 chlorine and the 2 oxygens, and the 1 chlorine and the 1 oxygen. They all have the same charge. All of them are -1. The only difference is the number of oxygens. We go from 4, 3, 2, and 1 oxygen. So they're all related to each other via those numbers of oxygens and the chlorine. So if we sort of break it up, for example, right about here, and if we go sort of this way, these are the guys that essentially have the least number of oxygens, which, as we just saw, should basically end in ite. So if we look at, for example, the ClO2 minus, we would call it chlorite. If we look at the ClO minus, which has the least number of oxygens, we would also perhaps call it chlorite. Obviously, we can't have two names that are the same for two different things. So in a group of 4, the one with the least number of oxygens will also start with hypo. So again, they'll both end in ite because they have the least number of oxygens there in a group of 4, but the one with the least out of that 4 will end in ite. And if we look at sort of the other side over here in that group of 4, we have our ClO4 minus and our ClO3 minus. Again, both of these have the most oxygens in that group of 4. So they both perhaps would end with 8. So this would be chlorate. And this would also be chlorate. Again, we can't have the same name for two different things. So the one in a group of 4 that has the most oxygens will start with per and also end with 8. So when you have a group of 4, the one with the most out of that group of 4 in terms of oxygens will start with the per and end with the 8. The one with the least number of oxygens will start with hypo and end with ite. And the two guys in the middle will essentially kind of follow the normal. The guy with the most will be 8. The guy with the least will be ite with no hypo or per on those guys. Any questions on that? What you'll also see when you look at this little table here is, in addition to chlorine, which is a halogen, you could pretty much swap out the halogen for any other halogen. So right below it over here, what we see is Br in place of Cl, and they're named the same way. This is hypobromite, bromite, bromate, and perbromate. Again, same thing if you swap out the Cl for the I, which is also a halogen, you'll get the same sort of distribution there in terms of the name. But probably the ClO4, ClO3, ClO2, and ClO minus on all of those are the most common polyatomic ion that you come across. So a good way to sort of group these together is to find the guys that are related to each other and remember, kind of memorize their names and their formulas and their charges. Sometimes what people will do is, for example, in a group of 2 or something like that, they will remember all the 8s. And what they know is the ites would just be 1 oxygen less. Or alternative to that, some people will remember all the ites and know that the 8 guy would be 1 oxygen more. So those are a couple good ways to sort of do it. Sometimes you don't have to memorize it all kind of individually. You can learn the 8s or the ites and know that if you learn the 8s, the guys that end in ite should be 1 oxygen less, or vice versa again. If you learn the ites, the ones with the 8s should be 1 more oxygen more. Now, although a vast majority of these polyatomic ions, as you can see here, essentially will end in either 8 or ite, there are some polyatomic ions that actually do end in IDE. So some common ones, cyanide is an example of that here, Cn minus ends in IDE. Also hydroxide, which is a polyatomic ion, also ends in IDE. You also have azide as well. So there are a few of these sort of polyatomic ions that actually will end up with IDE, kind of like what you see on the periodic table with those nonmetals, but a vast majority of them will again be your 8 or ite, but a few of those guys are the IDE. Now, there's a couple other things that you will also see with these polyatomic ions that sometimes happen. And if we look at, for example, grab a different color here. So if we look at, say, a CO3 2 minus, which is right about here. So if we look at CO3 2 minus, again, that's one carbon and 3 oxygens all together, never breaks apart, has a -2 charge. That is, as you can see down there, known as carbonate. And sometimes you put an H plus on it, or an H plus in front of it, and that gives us a form of HCO3 minus. Again, the hydrogen, the carbon, and the 3 oxygens are all bound together, has a -1 charge. Basically, you put the H in front of it, -2 and +1 gives us a -1 that's left over. And basically what we did is we put a hydrogen in front of it. So this is what is sometimes referred to as hydrogen carbonate. And hydrogen carbonate is also sometimes, instead of using the word hydrogen in a name like that, they will use bi and just call it bicarbonate. So very common, people still use bi instead of putting the hydrogen in front of it. They're both correct and used a lot, especially the bi is used a lot. You see that with carbonate. You also can see that over here as well. Let's see if I have it there. This list here. You could also see that a lot of times very commonly with sulfate. So we saw sulfate up here. Sulfate being SO4 2 minus. Again, if you put an H in front of it, H plus, you get HSO4 minus. This is again sometimes called hydrogen sulfate. Or again, this guy here is sometimes just called bisulfate. So again, that bi name is very commonly still used a lot by people in books and stuff like that. Any sort of questions on that there in terms of those? Again, you do need to know them, the formulas and the charges. In your book is a table of polyatomic ions, not this exact table, but a very similar sort of table to this one. And again, you need to know really the formula, the name, and the charges associated with them, because that's going to allow you really to sort of use these in chemical formulas. So for example, let's take a look at some of that. So because that ammonium, which is NH4 plus, is essentially the only positive polyatomic ion that you'll see, most of the time these polyatomic ions, the time, they are pretty much bound to a metal, which basically means we still follow, for the most part with polyatomic ions, those type 1 and type 2 rules, which means when these polyatomic ions are bound to a metal, the metal again is the important part there. That is what you want to look at. And just like we did for type 1 and type 2, if that metal is type 1, which means group 1, group 2, group 3, silver, lead, I'm sorry, not lead, silver, zinc, or cadmium, we don't need a Roman numeral. And if it is a transition metal, or just to the right, like lead, you do need a Roman numeral. So zinc, cadmium, and silver. And again here, if it's a transition metal, you'll need that Roman numeral. So if we look at an example, again, if we look at something like, for example, here, we go with CaSO4. When we look at CaSO4, we would break it apart right here. And what we know is our calcium is +2. This is one of those polyatomic ions, which is SO4 2 minus. So again, when we look at this, we have basically +2 coming together with -2. And again, that's why the formula looks like CaSO4. We only need one of each of them to do that. So again, here, the metal is the important guy. So our metal is from group number 2, which means it has a fixed charge. And that means that our name for this guy would be calcium, whole name of the metal. And again, here we would use the whole name of this polyatomic ion, which is sulfate. So this would be calcium sulfate. Any questions on that one there? Now, if we did get into something like a transition metal, for example, if I had FeNO3 2. When we look at this, again, we're going to look at this, which is iron. And iron is a transition metal, which tells us that we do need to figure out the charge, just like we did before, because it can have multiple types of charges. So when you do that, the next thing you want to then look at, just like before with our type 2, is we want to look at what it's bound to. And essentially, this is NO3 minus. And in this case, we don't have 1, but we do have 2. So just like we did with type 2, if we sort of add this up, we have -1, and -1 gives us a -2, which means to balance it out, the iron here has to be +2, which means to go to name this, we would do iron Roman numeral 2, again for the charge. And here, even though there's 2 of them, we still just name it like normal. We just use the polyatomic ion name, which is nitrate. So this would be iron Roman numeral 2, nitrate in this case. Any questions on that? So that brings up a good little point when we sort of look at putting formulas together that involve polyatomic ions. So the question was, why did we use, again, the Roman numerals here on the first one, on the second one, and not the first one? And the reason is, in this case with polyatomic ions, it is, again, the metal that's really important. So if that metal is in group 1, 2, 3, zinc, cadmium, or silver, it's just like a type 1 metal, like we talked about earlier, which means they have fixed charges. So you don't need to use the Roman numeral in that case, because something like calcium will always be +2 no matter what the deal is. It will never be anything different. In the second one, we do have iron here, and iron is a transition metal. So something like iron in certain cases can be +2 or +3. It has a variable type charge. So just like what we did with our normal type 1 and type 2, because this was type 2, we have to basically tell the person that's looking at it that in this particular case, we're talking about the iron that has a +2 charge, rather than, for example, the iron that may have like a +3 charge. So like I said before, because most of the polyatomic ions are negatively charged, they essentially will be hooked up with a metal. And essentially, you can follow those exact same rules for type 1 and type 2 that we talked about previously. Other questions on that? So what's important, though, when we do deal with these polyatomic ions and sort of putting them together for our formulas is, as we can see here, when we take something like iron with a +2 charge and our nitrate with a -1 charge, when we put them together, just like normal and just like an ionic compound, we want to make sure that it is equal to 0. So this does mean, as we can see in the formula to the left there, that we do need not one of these nitrates, but we do need 2. So when we put them together and we write the formula, we don't want to write it just like this, right? What that essentially would imply is, if you don't put the parentheses there, it essentially applies that you have 1 nitrogen and 32 oxygens, basically. And that's really not what you're trying to do here. What you're really trying to say is, as you can see up here, you have 3 and 3 is 6 oxygens and 2 nitrogens. So whenever you have more than one polyatomic ion, You do have to put parentheses around the polyatomic ion, and you do have to put the little number there on the bottom to indicate how many of those polyatomic ion units that you have. And so whenever you write the formula for something that involves more than one polyatomic ion, that's when you got to put the parentheses around it and that little number on the bottom to indicate how many you have. If you just have one, like we did over here on this side where we had the calcium sulfate, the parentheses are not needed here because it's just one. So it implies there's just one of those units. So typically speaking, people do not put the parentheses around just one polyatomic ion. They'll write it like it was originally, something like this. But definitely if you have more than one of those polyatomic ions, you do need to include the parentheses and that number on the bottom, basically to tell everybody that you have, more than one of those polyatomic ion units. Any questions on that? Okay, so let's take a look at some examples. I'll write some up here and give you a chance to sort of go through them, and then we'll talk about the answers for these. So why don't you name the following? So let's do name following. So let's go with let's do that one. Let's do that. And then why don't you write the formula for these guys? Take a couple of minutes here and try them. Let's do potassium hydroxide. Let's do three sulfite and all right, so why don't you take a couple of minutes here and try to work through these, and we'll talk about the answers in just a second. All right, so let's take a look and see how we're doing. So coming here at this first one, let's go up this way. Again, when we look at this, we have barium and CO3. So barium, which is group 2, which is Ba with a +2 charge. CO3, again from that table, is CO3 2 minus, which is carbonate. And again, when we look at those charges, really our cation here is our barium, our anion is our carbonate, +2, -2, which is why we just need one of each of them here in the formula. And so because barium is type 1, it does not need a Roman numeral because it has a fixed charge. So this would be barium. And then for the polyatomic ion here, we just use the whole name from that table, which would be carbonate, AT. Any questions on that one there? Now, when we look at the second one here, again, we want to kind of take the same approach here. We got Cu, which is copper, and we have SO4, which is sulfate. So copper, which is a transition metal, means we're not sure what the charge is. But again, once you learn from that table, SO4 is SO4 2 minus. So just like what we've done before, when we see the copper there, is a transition metal. It means, again, it can have a variety of charges. So to figure out the charge here, it is -2. But in this case, we don't have just one copper. We do have two coppers. So to balance it out, actually, each copper in this case is going to be +1, which will give us a +2 overall. And that means that this name would be copper Roman numeral, Roman numeral 1. Turn that into a parenthesis. And again, here we'll use the entire name for our SO4, which is sulfate. So again, although there are two of them, remember that the Roman numeral indicates not how many metals you have, but it indicates the actual charge in each individual metal. So this would be copper 1 sulfate. And looking at the last one here, we have nickel, which again is a transition metal, so that's type 2, the big circle. And again, here we have basically 3 nickels. We do know that this is a polyatomic ion, which is PO4 3 minus. And same thing here. We don't have one of them, but we do have 4 of them. So I won't write them all, but 4 times -3 gives us an overall -12 charge, which means that each of these nickels, in order to balance it out, would need to be +4. Right? And that would be 4, 8, and 12 positives in terms of the charge. So again, just like what we did with our regular ionic compounds, just like we did balancing out the charge, we want to figure out what the charge is. And that obviously will affect the name here. So it will be nickel Roman numeral 4, again, because the charge on each of those metals is +4. And even though we have 4 of these phosphates here, it will have no effect on the name. We're just going to use the whole name there, which is phosphate. Any questions on any of those 3? So the nickel, the question is, why does nickel go up so high? Sometimes it can. A lot of those transition metals are those guys just to the right. For example, lead, which is not really transition metal, but if you look on the periodic table, it's just to the right of it. Lead, for example, could be lead 2 with a +2 charge, could also be lead 4. So common charges that transition metals and those guys like lead, tin, and stuff like that, a lot of times +2s, +4s, +3s, those are some common type charges. And that's why we do on those guys has to indicate the Roman numeral, because they could potentially be some other charge. But for our purposes, things could technically go up to things could technically go up to, for example, +6 or something like that, but common sort of charges +2, +4, and +3 are very common. +2 and +3s are really common. So I think the question was back to the second one there. Why is it copper 1 versus, say, copper 2? And it does has to do with what it's bound to. So when we looked at this guy here, because this guy is bound to sulfate, which has a -2 charge, and in this case, in this formula, we have not one copper, but we actually have two coppers. Each of those individual coppers will end up with a +1 charge. So that'll give us +1 and +2 overall. And that would balance out with the -2 charge. So again, remember that when we write the Roman numeral, it's for the charge on the metal. So it's really the positive charge on the metal, not how many of those metals that you have, which is a very common thing that people sometimes think is they see, for example, in that formula, they'll see the 2 here and go, oh, I got 2 coppers, so the Roman numeral should be 2. And it's not it's not how many you have, but the actual, if you just took one of those metals out, what the actual positive charge would be on one of those metals. Other questions on this? Okay, so then let's go to the other side. And on the other side here, we're looking for the actual formula. And when you have the name and you want to write the formula, you always want to start with really the basics. And the basics are what the two, for example, ions are here. So when we look at potassium, I'll go this way, save some room. Potassium, which is group 1, has a +1 charge. Hydroxide is one of those polyatomic ions, although it does end in IDE, is one of those few polyatomic ions that do end in IDE. And if you look on that chart, it is OH minus. Again, a reminder, all polyatomic ions, those guys stay together. So that one oxygen, that one hydrogen has an overall charge of -1, while our potassium here has an overall charge of +1. So it is essentially an ionic compound. So just like normal, to get to 0 with both of these guys, we basically just need one of each. So we would just write KOH. Again, meaning that potassium is +1, OH is -1, +1, and -1 will get you to 0 in the overall charge. Now, when we look at the second one here, which is iron 3, the name here actually gives us a lot of information. So as we were just talking about the iron, it was Fe. And again, what the Roman numeral 3 is not how many you have, but it tells you that that iron has a +3 charge. So just from the name alone with that Roman numeral, it will tell us that it is iron with a +3 charge. Now, when we look over here to sulfite, the key here is it does end in ITE, which means it's actually SO3 2-, not SO4 2- like sulfate over here. It is SO3 2-. And again, same idea. When we put this together, this SO3 has a -2 charge. Our iron has a +3 charge. So when we put it together, sort of the common number there is 6. And to get our iron to become 6, we would need not one of them, but we actually would need 2 of them. 2 times +3 is +6. And to get our sulfite to 6, we actually need 3 of them. But here, if I don't click the wrong button there, come back. There we go. If we look at our SO3 2-, we need 3 of them. But because it's more than one polyatomic ion, this is a case where we have to put parentheses around the SO3. And because we need 3 of them, we would put the 3 at the bottom. And that indicates that we have 3 of the SO3s. And that's at -2 each, gives you a grand total of -6. We have 2 of these irons, each at +3, gives you a +6. So obviously plus 6 minus 6 will get you to 0 in terms of the overall charge. So although these are polyatomic ions, they're groups of nonmetals together. There's a lot of them kind of involved. It's really still the basic idea that if we put something that is positive and negative together, we want to make sure that the overall charge equals 0. Any questions on that one there? Okay, and looking at the last one here, again, aluminum has a +3 charge as its group number 3 on the periodic table. Our cyanide, which again is from that polyatomic ion sheet, is Cn minus. So now when we put this together, again, the carbon and the nitrogen has a -1 charge. So to balance it out here, we actually need 3 of these guys over here. So our formula would be Al, again, because it's more than one polyatomic ion. We need to put some parentheses around it and a 3 at the bottom to indicate that we have 3 of these CNs, each at -1. So -1, -2, -3 to balance out the +3 charge that we see over there. Any questions on polyatomic ions or how to write the formula, how to name them? They're essentially, like I said, because they pretty much will be hooked up with metals, you pretty much could just follow the type 1 or type 2 rules that we talked about earlier. The only difference is, again, just like in type 1 and type 2, for that second one, that if it is a polyatomic ion or the second sort of polyatomic ion in that formula, even if there is more than one, we still just use the whole name of the polyatomic ion. So again, as we saw over here, we do not use anything like tetra or any type of prefix, even though there's 4 of them. We just use the entire name here of the polyatomic ion, regardless if there is more than one of them. Same thing as you can see here, even though there is 3 of the cyanides here, when we did name it, it's just cyanide. Same thing here, there's 3 of the sulfites. The name is just sulfite. So no prefixes involved with the polyatomic ions. And what I mean by that is, and I'll just go back to that little slide there, I think. There are some polyatomic ions that actually have prefixes built into their name. So dichromate's an example. That's the only time that sort of a prefix will sort of be used with a polyatomic ion, is if it actually is part of the actual name of the polyatomic ion. But if it's not part of the name of the polyatomic ion, you definitely shouldn't use a prefix or anything like that. Any questions on how to name polyatomic ions, write the formulas? Okay. All right, then the next thing we're going to talk about is acids and sort of how to go about naming acids. And acids are basically substances that, when they are in water, they're able to produce the H+ ion, which is sometimes referred to as a proton. And what that essentially means, for example, is something like HCl, which is hydrochloric acid. When it's in water, it produces H+ and Cl-. And because it produces this H+ in water, it's considered basically an acid. And in terms of how we name acids, there's some rules in terms of how we name them. But before we do, let's just talk about sort of the difference here between, say, something like this and something like this, which is a good step. If we have something like this, which is, say, in the gas state, which is HCl, and it's the same formula as we see up here with the AQ. The difference between these two and how we name it really is in those little states. So G means gas, AQ means aqueous. And if we were to name something like this, we think of this as H+ and Cl-. And in the gas state, we basically will just call this hydrogen. So whenever you have a hydrogen that comes first, that's not an acid, we would just call it hydrogen, and this would be named like normal, and this would be chloride. So that would be hydrogen chloride. We had H2S that say was a gas. Even though there's a 2 in hydrogen, it's a little bit different than most things. Even though there's a 2 here, we would still just call it hydrogen. And the S comes from the periodic table, ends in IDE, would become sulfide. So to go back to sort of type 1 type compounds, if you have an ionic compound that has an H in front of it and it's attached to some type of negative ion like we have there at the bottom of the screen, you would just call it hydrogen, regardless if there's 1 or 2 sort of hydrogens involved. Now, if we take that same formula like we have here, and we put the aqueous symbol next to it, typically the aqueous symbol is the symbol that goes with acids. And that's how you recognize something that's HCl that has the aqueous next to it as an acid versus something that is HCl that has the G next to it, which is a gas. So if it is an acid, we do actually name it differently. So for example, the HCl there, just add it up here, with the aqueous next to it is what is known as hydrochloric acid. So especially when we get to acids that do not have oxygen in it, there is sort of a crossover in terms of sometimes you'll see the same formula but different names. And again, this is basically the gas form of it. Truly, if they take this gas and put it in water, you get this, and that becomes an acid. And that's really what aqueous means. It means basically a water environment. And basically what it means is usually that is something that you took and dissolved it in something, for example, like water, and you make a lot of times a solution. So if you kind of run hydrogen gas in water, you'll make some hydrochloric acid, which is a solution. Any questions on sort of that distinction? So when we talk about acids, in terms of naming acids, it's really all about oxygen, and oxygen is really important in terms of how we go about naming acids and the rules for it. So when we talk about acids, it all has to do really with oxygen. So if the answer is you have no oxygen, when you go to name the acid, it will always start with hydro something ic acid. So for example, the one we just saw on the previous page, HCl, again, typically we'll have that aqueous symbol next to it. No oxygen involved here. So we will start with hydro, and then the middle part is the anion, or the negative guy. So hydrochloric acid would be this guy. If I take HBr, for example, again, when we look at this, there is no oxygen involved. So we would start with hydro. It'll be hydro, Br is bromine. So hydrobromic acid is what this would be. So hydro and acids, and people for some reason always want to use hydro on every acid name, but hydro part of it in terms of the name is really only used when you have an acid that does not contain oxygen. So for some reason, people always want to throw that hydro part of the name in with like every acid that they see, but it's only for those guys with no oxygens. So let's talk about then what happens when we do have oxygen involved. So when we do have oxygen involved, here. So if we go this way, the answer is yes to oxygen. It is going to most likely contain a polyatomic ion like we were just talking about. And if you remember, those ions ended mostly in ate or ite. And recognizing those polyatomic ions in the acid name is going to be helpful to be able to correctly identify it. So, or the formula. So if we look at it here, we'll go this way. So if the answer is yes, and that polyatomic ion ends in ate, the acid will be something ic acid. So for example, if we look at HNO3, again, here we see the aqueous, which indicates that it is an acid. We do see oxygen involved. And when we see oxygen involved, we see NO3. And as soon as you remember those polyatomic ions, you'll remember that NO3 is nitrate, AT. So because it's nitrate, it will become nitric acid. I see. Again here, because it contains oxygen, no hydro in that name. So hydro only for guys with no oxygen. If we look at something like H2SO4, SO4 has oxygen, and SO4 again is SO4 2 minus, which is sulfate. So the name of this acid would be sulfuric. I don't hit the button there. Sorry again. Sulfuric acid. So a good way to remember it is I ate too much, I feel icky. So that's a good way to kind of remember in terms of the acid how to name it. When we look at this formula, though, what essentially makes everything an acid is H plus. Yeah. So H plus is essentially the cation for all acids. And that's why when we put H plus together with our sulfate, -2 and +1, we end up with the 2 hydrogens that's needed here. So in terms of the formula, we need the 2 hydrogens to balance it out. So if it does contain oxygen and it contains a polyatomic ion that ends in ate, we want to go with ic and then acid. Now, the other type of polyatomic ion, for example, is we'll go down this way with it. So if the answer is still yes to oxygen and the polyatomic ion ends in ite, then the acid name is something OUS acid. So if we take HNO2, for example, NO2 here is NO2 minus, which is nitrite from that list. And again here, our H, which is our cation, is H plus. And because it's ITE, we will follow this route here and end in OUS. So this becomes nitrous acid. Yeah. Also, if you had something like H2SO3, again, the SO3 here is sulfite. So this will be called sulfurous acid. So really when we're naming acids, it's really all about the oxygen. And the oxygen, if there is none, that is the only place for acids that you should use hydro. If it does have oxygen, it's going to contain one of those polyatomic ions, and you would use either ic if the polyatomic ion ends in ate, or OUS if the polyatomic ion ends in ite. Question on how to name or write the formulas there for acids. Let's see here, may I put some up there? Yeah, let me put some up, just give you a chance here to try some. So why don't you give the name of these acids? So why don't you give a name for those acids, and then let me see here. Why don't you give the formula for these? All right, so we're looking for names up here. And then formulas down here. I'll give you a couple of minutes there to kind of go through those, and we'll go over them. All right, so let's take a look and see how we're doing on some of these. So again, here we look at this, we see the aqueous, that automatically sort of indicates that it's an acid. We also look and there's no oxygen. So that means that it should start with hydro. So we'll have hydro. The second part is based on the anion, which is I. So this would be hydroiodic acid, again, based off of iodine. Taking a look at the next one here. Also the same situation. We don't see any oxygen here. So we know that's going to start with hydro as well. S, which is sulfide, becomes hydrosulfuric, again ending with the IC and the hydro at the beginning, and acid. Any questions on those two? All right, so going to the right there, we do see in this case some oxygen. So it's yes to oxygen, which means we need to determine the polyatomic ion that's present, and that is CO3 2 minus, which is carbonate. So because it ends in 8, we're going to use the first part of it, which is carbonate. So it's going to be carbonic acid. IC. Again here, because it has hydrogen, no hydro in front of it. So just carbonic acid on that one. And looking at the next one, also we see oxygen. So we want to identify that polyatomic ion. Again, this will be much easier once you sort of learn them. So ClO4 minus, that is our perchlorate. That was that group of 4 that we talked about earlier. And that means we still keep the per here because that's part of the polyatomic ion name. So this becomes perchloric acid. And again, in this case, in all these cases, the cation for the acid is H plus. And that's why up here we need 2 of them to balance out the charge, while here we just need 1 of them to balance out the charge because this is -1 and +1 will equal 0. So this would be perchloric acid. Any questions on any of those 4 there? So question is, it has hydrogen or oxygen? So all acids essentially are pretty much made up of, all acids are made up of H plus and some type of anion, which is our negative ion. And basically what makes up an acid is always that H plus because that's what it's able to pretty much produce. So the anion is really where we get the difference in terms of naming. If this anion has no oxygen, then that's when we use the hydro. And if this anion does have oxygen, that's where we don't use hydro, but it ends in ic or us, depending on the polyatomic ion. Other questions? So when we're coming down here to actually write the formulas, we see hydrofluoric acid. So the hydro right off the bat tells us that it does not contain oxygen. What we do know, as I just mentioned, all acids, the cation is H plus. So we could deduce from that, if it doesn't contain oxygen, it's probably going to be from the periodic table. And fluoric sounds like fluoride, which would be F minus. So putting this together, we have +1 and -1. We just need HF. And again, typically you would put the little aqueous symbol next to it to indicate that it is an acid. Any questions on that one? So when we sort of deconstruct this last one here, we see phosphoric acid. We don't see hydro, which means it does contain oxygen to this bottom one. And because it ends in ic, what we know is that the polyatomic ion should end in 8, which means if you just take the first part of the name here, phos, and you add the A to it, that should get you to phosphate as the polyatomic ion that's involved, and that is PO4 3 minus. Again here, every acid, the cation is H plus. So what we could do here is when we put it together, we want to make sure it equals 0. So in this particular case, we actually need 3 of these H pluses to balance it out. So that will get us a formula that is H3PO4. Again, putting the aqueous next to it, and that would be the formula for phosphoric acid. We have 3 of the H's at +1, +2 with the second one, and +3 with the third one here to balance out the -3 charge that we see in the phosphate. Any questions on that? Any questions on naming acids, writing the formulas for acids? Again, you do need to obviously be able to do that as well. So in terms of chapter 3, that technically sort of completes chapter 3 in terms of naming. But what I did put on these notes is from chapter 4, which we're going to talk about next. So we're technically transitioning into chapter 4, but it's still naming. So it kind of went good with all the stuff we're talking about here. So we'll continue on to really this part of naming which will involve chapter 4. So in chapter 4, we're really going to be talking about different types of compounds, and these compounds are what are referred to as covalent compounds. And the difference between ionic compounds, which is mainly what we were talking about there, and covalent compounds, is that typically it's between two nonmetals. And here we do have sharing of electrons. So if you remember, in an ionic compound, like we talked about mostly in the previous chapter, that is usually between a metal and a nonmetal. And we don't have sharing of electrons, but we have a transfer of electrons. And basically we create a cation that's attracted to an anion with no sharing of electrons. It is just that attractive force between those two ions that basically hold those things together, as opposed to in a covalent guy where we actually do have the sharing of electrons. So we're going to finish up here talking about naming these type of guys that are covalent. And those guys are sometimes referred to as type 3 compounds. And type 3 compounds, as I just mentioned, basically two nonmetals. And these are really the easiest ones out of all of them to sort of name and sort of write the formulas for. But it's also the ones that people really kind of screw up a lot of times because they're trying to do all kinds of things that they shouldn't, like balance charges or things like that. You don't have to worry about charges or anything when you get to these type of guys that are two nonmetals together. But before we get there, there are some things that do have common names and always sort of go by their common names. And a couple of those guys, for example, H2O. H2O is water. It's not a trick question. You should put water down. H2O, which is water, it's not dihydrogen monoxide. Most people don't want a refreshing glass of dihydrogen monoxide. So if you do see H2O, it is just called water. NH3, and this is different than that polyatomic ion. It has no charge. So NH3, no charge, is what is known as ammonia. And not to be confused with what we saw in the polyatomic ion, which is NH4 plus. Again, the difference is there, one more hydrogen and a plus charge, which is the ammonium ion. So this is an ion. This guy is not an ion down here, has no charge, and is has only 3 oxygens. So that's very common, two things that get confused a lot. And probably the last one for us, CH4, is a common name. That's the simplest organic molecule you can have. That is methane. It's kind of like what happens when you light a Bunsen burner, for example, in the lab. You turn on the gas, make a spark, and you get methane. So when we name these type of guys, which are type 3, again, they're pretty much the simplest ones. If you do come across these 3 guys on the bottom of the screen, the water, the ammonia, and the methane, those are the names that you should use for those. But let's talk about everybody else that's sort of type 3. So when we name type 3 guys, we essentially will use prefixes. So here we use prefixes. We'll see a list in just a second, like mono for 1, di for 2, tri for 3, tetra for 4, and so on. And this is actually the place where you should use prefixes, not in where most people want to use prefixes in all the wrong sort of places. You do actually want to use them here. A couple of things with the prefixes. We pretty much will name these guys by using the proper prefix plus the whole name of the first element, and then the prefix and the next element named like a normal nonmetal. It will get the IDE at the end of it. Now, one of the rules is we don't use mono on the first name, but you can use it on the second name. So that's perfectly fine. First name, you can use don't use mono, but the second name you can. So for example, if we look at something like CO, this is a carbon, and an oxygen. That is two nonmetals, and you should be really happy when you see that because you don't have to worry about charges, you don't have to worry about balancing anything. You pretty much just need to count what's there. So there's one carbon, there's one oxygen. Prefix for one is mono, prefix for one is mono. But as the rule says down here, we do not use mono on the first name. So if we were to name this, we just use the whole element, which would be carbon. And then the second one is oxygen, which we would name like normal, becomes oxide at the end. But we do put the prefix on the second one, and this would become monoxide. So carbon monoxide is where this name would be. And this brings up something that happens with prefixes. So for example, if I wrote the prefix for the second guy and then the anion name, we would get monoxide, which is not really the name that we use for that. So very often when you're using prefixes, if you get these two O's that back up to each other, we typically drop off the O from the prefix like we did up here, and we end up with a name like carbon monoxide. Also happens when you get a prefix that ends in an A and an O. We typically will drop the A off of the prefix when we name it. So for example, if you had 4 oxygens, it would be, instead of TETRA, we would drop that A off of tetra and just do tetroxide there without the A involved. So those are two sort of things that happen with prefixes. You oftentimes will get a couple of vowels that are next to each other and we will drop it off. So if we look at CO2, same idea. We only have one carbon. We have 2 oxygens. So again, no mono on the first name. So carbon and dioxide here for the 2 oxygens. So this is definitely the place where you should use those prefixes, is when you have 2 nonmetals together, and it's basically how many use the proper prefixes. Any questions on that there? So here's just a table that those prefixes again: mono for 1, di for 2, tri for 3, tetra for 4, penta for 5, hexa 6, hepta 7, octa 8, in case you ever get up there, nona for 9, and like deca for 10. Probably won't get up there too much, but you know, you might in terms of that. All right, I'm seeing we're getting close to the end here, so it's probably a good place to stop and talk about a few things about what's happening next week. But before we do, any questions on the stuff that we are talking about now? So again, we've now really transitioned into chapter 4. So we technically finished chapter 3. We're into chapter 4. So there's another handout up on Canvas that is the rest of chapter 4. So the handout that we're using right now just talks about the naming part of chapter 4. And then you'll find an additional handout up there on Canvas for the rest of chapter 4, which is basically bonding, Lewis structures, and that type of stuff we'll talk about next week. Any questions on any of this stuff? Okay, so next week, I believe should be our first exam. We're going to give it a go, and it's going to happen on Monday. So my plan is, as of now, I'm not going to lecture on Monday, but the exam will be available probably around 7ish or so, around our regular sort of lecture time. And it'll be available in that time period from 7. I'm not sure exactly when it'll be available, but it'll be definitely through our lecture period for sure, for you to take the exam. And again, I'll send out a message up on Canvas. I can't promise I'll get it before the end of this week, but at least maybe over the weekend or something, definitely before Monday. They'll have more detailed instructions about the exam, but it will be available for you to take on Monday. You will log into Canvas, and it will be probably under the quiz section, or I might make a module that will link you to it, but you will take it on Canvas. Couple of reminders that when you take the test, obviously just like in class, it should be your own work. It should be you that is taking the test. You should not be using any type of notes and stuff like that as well. So kind of the honor system and all that good stuff here. It does need to be you, and it's just like normal testing conditions. You shouldn't use notes. You shouldn't use your book. You should use your calculator and your knowledge. So, with that being said, you want to be completely ready to take the exam when you're ready to start it. There will be a time limit. So once you click to start the exam, you'll have sort of a countdown clock that will be on there that you can see. And once you start, the clock will not stop. So you can't like pause it and come back to it or anything like that. You have to kind of answer all the questions within that allotted period of time, just like you would if you were sitting in front of me in the classroom and taking it. You know, you would have the whole period to take it in lecture, and then obviously you would have to be done with it. So very important to make sure that you have everything that you need for the exam before you begin. So that should be your calculator. I'm going to try to obviously provide you with a periodic table. I definitely will put it up there somewhere for you to use. And in the questions and in the exam, there will be conversion factors given to you for questions that you need conversion factors for. I think at this point, it'll be somewhere on the exam, but I think just to make sure you can find them, I may just insert all those conversion factors and stuff into each question that you might need it for. And if you do see the conversion factors in a particular question, it does not necessarily mean that you have to use them or all of them or any of them. It just means that they're there for you to kind of find easy without having to click around and look for them. So like normal, anything that's a conversion factor will be provided for you. And like we talked about in class, you do need to know formulas. So like D equals M over V, that will not be provided for you, nor will the conversion for temperature be provided for you as well. You want to also make sure that for each question and the instructions at the beginning of the exam that you read it very, very carefully. Yeah. Because they may tell you to do certain things and problems. So you want to make sure that you do read each of the instructions really carefully, that you don't miss anything. Because it is a chemistry class, and because, like I said, we have to do it sort of online here, I want to have the opportunity to try to give you some partial credit just in case the answer that you put is incorrect online. So with that being said, being prepared to take the exam before you begin, you probably need some paper, and there will be problems where you will have to show the work. So you'll have to show the work, the setup, the units, the significant figures, and the answer. And once you complete your exam, you will have a certain amount of time, because I'll know exactly when you're finished your exam. You'll have a certain amount of time, obviously, to upload the work part of it. That way, in case the answer that you put online is incorrect, I at least can kind of go back and try to look through your work and give you some points. So I'm trying to make this so it's not an all or nothing type of thing, like an online sort of question. So again, even if you happen to miss the answer online and you upload your file with your work, then I will be able to at least hopefully go back and assign you at least some points for that question. So that should also be something that you should be prepared with. And in terms of those notes, you got to do your best to make sure that it is labeled correctly. It is clear that I could understand what you wrote there, and you do need to upload it. So again, to upload stuff, there's all kinds of ways you can do it. You can scan it in. I do know, just for example, Adobe has some phone apps. I think it's called Adobe Scan for iPhone and Android, which I think is free. And it basically will allow you to use the camera on your phone to kind of scan all your papers and save it as a PDF, which might make uploading it a lot easier as well. So there will be a spot up on Canvas, probably in the assignment section, where you'll be able to upload, after you've completed the exam, your work. Obviously, that will be uploaded at the same time period after you complete the exam, not like 2 days later, 3 days later, like here's all my work after you redid everything on the paper. With that being said, just so we're clear, you do need to enter an answer for all the questions online, and the work that you will upload should match the answer that you get online. So if you do not enter an answer for a question online, I will not look at the work part for that particular question. Again, the work is supposed to sort of complement the answer that you get online. You can't also just say, I worked everything out on the piece of paper without answering anything online. You do need to answer it online. And then obviously on your work, on your paper, you need to show your work and upload it with the answer, proper setup, and significant figures. Now online, because it's online, there is sort of a limitation perhaps to how I can answer or how you can answer the questions. So make sure you follow those instructions, because it may say, hey, give the answer to 4 decimal places or something like that. So just follow those. But on your work, you should try to follow our normal rules on sig figs and all that. Any question on sort of the exam? And again, my plan at this point is not to lecture, so that should hopefully free up this time period for you to take the exam and get it out of the way for you. And again, I will send, the exam is going to be through Canvas, so you'll log on to Canvas, and there should be a section, and all those sections like modules and stuff like that. There'll probably be a section that's called quizzes, and that's where the exam will be. And I will also, I think, maybe make like a module or something to make it really easy and link it to take you right to the exam. But again, before you start that exam, make sure you have everything that you need: calculator, paper to do just the work on, and all that kind of stuff. Because again, once you start it, the clock keeps going and there's no way to pause it. With that being said as well, you want to make sure that when you're completed with the entire exam, you want to make sure that you actually submit it. Yeah. So I think after the very last question, actually you'll be able to see all the questions at once, I think is how I'm going to set it up. But you do want to make sure that you hit submit when you're completely done. So don't hit submit for the entire exam after you do one question, but make sure that you answer each question kind of individually. And then when you're done with the entire exam, make sure it's important that you actually submit it to me. Otherwise, I won't see your answers or anything like that. The question again is, like we talked about, the exam is going to cover just the first 2 chapters like it was scheduled to do normally. And we'll cover just those first 2 chapters, so 1 and 2, just like it was previously. That also means that the online homework should also be due pretty soon as well. Any other questions on any of that? Again, I will send an announcement on Canvas, before Monday. I can't promise what day, but before Monday, again, kind of detailing everything as well. Any other questions about the exam? So again, no lecture on Monday. So again, that will free up this time period, hopefully for you to take the exam. I will also let Dr. Tyler know that the exam's scheduled for Mondays. So if you have Monday lab, I'm not sure what her plan is for Monday, next Monday, but I'll let her know that we're taking the exam, so she'll be aware of that as well. And then we will continue lecturing back on Wednesday live at 7:35, and we'll continue through chapter 4. Any other questions on anything? Okay, so again, make sure that you definitely check your email, check the Canvas site throughout the rest of the week, and obviously through the weekend before Monday, again, so you can get hopefully that announcement about the exam and how to do it. And other than that, that should end it for today and the week as well. I think it's Wednesday. So have a good rest of your day. Again, if you have Monday lab, I think you might be, or Wednesday lab, you might be off to lab. So have a good one. And then I'll virtually see you again officially on Wednesday. But again, the exam is on Monday and you do have to take it on Monday. Okay. All right. Have a nice day, everybody. I'm going to officially end this one, and I'll see everybody next time. Thank you. Have a good day too.